Thank you for joining me. Good afternoon. I hope you enjoyed lunch. We're going to talk about functional programming today in JavaScript, and we're going to utilize the new ES6 syntax and use that to explore some functional concepts, some of the basic things about functional programming, and see how we can capitalize on some of the new syntax and features to actually write cleaner functional code. So my name is Jeremy Fairbank. I have a blog at blog.jeremyfairbank.com. And if you want to follow me on Twitter, I'm Papapoyo and jfairbank on GitHub. Just very briefly about me, I work for a company called CGET. We're a completely remote team focused on design and front-end development. And in addition to being an agency, we have our own product called Simply Built, which is a website builder and editor, along with domain management and hosting. So, primary reason we're here today is because of libraries like these and this sort of renaissance that's been happening in the JavaScript world over the past few years. And it's functional programming has been showing up and more, and I think it's very important to understand why these libraries are cropping up, why functional programming has becoming so important. We have React and Redux and some reactive things like RxJS, Bacon.js, and lots of other libraries. So today, what we want to explore is, what is functional programming? What does that actually look like? Correct our score on my screen. And what would that be like compared to procedural style programming, object-oriented programming? So the bigger question, though, is why functional programming? Why would it be important? Why would we want to utilize it, incorporate it in our tool belt as programmers? And so we're going to explore both of those things and see what it looks like, why it might be useful to us. So I want to start off just thinking about basic building blocks. When we think about this is functional programming, the word function is in it. And as you might think, functions are going to be our building blocks. They are the atomic pieces that all of this hinges upon. We're going to use just functions to build up very complex, higher order patterns to write very elegant and hopefully more error-free code. So to start off, what is a function really? If we go back to elementary school math or middle school math, we might have seen something like this, where our teacher told us it's a unique mapping from the domain to a range. We have two different sets. And that might have been a little esoteric or confusing. And then we might have gotten something a little more like this. F of x equals x plus 2. And so that kind of clicked. It's like, oh, okay, this is just something that takes an input, we do some computation, and we produce an output. We understand that. If I pass in 2, I get 2 plus 2 equals 4. If I pass in 3, 3 plus 2 equals 5, and so forth. But when we begin to look back at that earlier definition, we see an important property about these functions, especially in math. Our input, those are our arguments, that is the domain. We have a set of numbers that can go in. And then we have a guarantee that each of those inputs is going to map uniquely to some sort of output. So that's the return value from a function. That's our range of values. And so we see how those two things tie together. And so there was this guy named Alonzo Church who kind of capitalized on this idea of modeling computation in terms of these pure functions. And he was actually a professor of Alan Turing's. So while Alan Turing was developing these modes of computation based on the Turing machine, Alonzo Church actually approached it from a different angle, where we could express computation in terms of just small units of expressions called lambda expressions. And so he developed what is called the lambda calculus, and it's a Turing-complete language itself. And so we're going to build upon those very basic mathematical ideas of just representing computation from small units of expressions, lambdas, functions, to explore functional programming in the world of JavaScript. So if I had to distill this down into some principles, sort of like solid from the object-oriented world, I would say we have 4 principles, at least within the context of this discussion. And so the first thing I would say about functional programming is that it's predictable. And what that means is we have pure functions, and we have declarative style programming. And that gives us certain guarantees where we have better determinism. I have guarantees that since I have a pure function, I know that if I pass this in, I will always get back some exact output every time. And so this gives us certain guarantees on predictability. We also have safety. And this comes a lot from immutable state, in that I don't mutate state, I keep immutable state, and if I need to change it, then I'll just create new state. And that's going to protect me from slight typos and other errors that could crop up from mutable state. In addition to being safe state, we also want it to be transparent. So we want our state to be out in the open. We want functions to compute on this data out in the open. We don't want to stuff it behind objects that we just send messages to. And so we'll explore that as well. And then finally, the idea of modularity. And this goes back to the idea of functions as building blocks, that we can take these small pieces and we can start piecing them together in different ways through things like querying, partial application, to build up much higher order patterns. And so it empowers us to deduplicate our code and have very modular code through functional programming. Now, before we really dive into it, let's go over some of the ES6 syntax that we're going to utilize today in our code and just get a feel for how we're going to utilize it. So the first thing we have are new variable bindings. Before, we always had the var statement to declare our variables. Now we have let and const. And the difference from these with var is that they are block scopes. So with var, you know, no matter where you place it, it's going to get hoisted up to the top of a function scope. In this case, with const and let, they're just going to be inside block scopes, and they're not going to leak out of that. And then the slight difference between let and const is let is kind of like the new var, in that I can assign a value, and I can always reassign it to a different value. Whereas const is a constant binding. Doesn't mean the value itself is constant, but the binding is constant, which just means once I assign a value to it, I cannot assign a different value to it later. That would be a syntax error. Of course, we're talking about functional program. We've talked about lambdas, which are anonymous functions. And so we're going to have arrow functions, which are one of the biggest things that came with ES6. So with an arrow function, we have, again, parameters in parentheses. But now we separate the parameters and the function body with an arrow. And then we can still have a normal looking function body. We have our braces, we have a return statement, and so it's very similar to function declarations and function expressions that we already had before. We can also eschew a couple things, such as the parentheses and the braces. And in this case, with this identity function, if I leave out the braces, that means that this function has a single expression as its body, and it's implicitly returned. So I don't have to explicitly put return x here. And notice also, if I have a single argument, I can also leave out the parentheses and just have x without parentheses. And so this is just a simple identity function to highlight how we can write very succinct, simple-looking arrow functions. Another thing we can add to our functions is utilizing the rest spread operator. And it's the 3 dots ellipsis operator. And when we use it in parameters, it allows us to represent that this function takes a variable number of arguments. In this case, I have an array function. It takes a variable number of elements, and then I'm just going to re-return those elements because they're going to get placed inside of an array when I use this rest operator. So I call array on 1, 2, 3, and I get back a literal array with 1, 2, and 3 in it. I can also use this as a spread operator. So in addition to gathering up variable number of arguments, I can also pass variable number of arguments into the function. So I can just gather up my arguments here, pass them back into console.log. And so this is a nice, cleaner way of doing the old method of calling the function's apply method, where you could pass variable number of arguments in that way, and that's something from earlier versions of JavaScript. So here I can just pass in variable number hello, Scenic City Summit, and all those get passed into console log. Another thing that we'll utilize some is destructuring. And if you are a Python person, a Ruby person, and I'm sure there are other languages that utilize this, it's this idea that I could take a complex data structure, like a list, an array, a tuple, and I can pull out multiple values from it and put them in different variables. So in this case, I have an array of languages, JavaScript, Ruby, Haskell. And I can pull out individual elements by assigning it to this const with the braces, JS, and then using that rest operator again with a rest variable name. And so what that basically does is it's saying, take the first item, which is JavaScript, assign it to the JS variable binding. And then I use the rest operator, and that's saying, take whatever else is left in the array and just stuff it in this rest variable. And so that gives me JS is JavaScript, REST at the first index is Ruby, REST at the second index is Haskell. I can also use this in my function parameters. So I can have a head function, and it takes an array, and its purpose is just to return the first element in the array. Well, I could just utilize destructuring here and say, pull out the first item, go ahead and assign it to the binding x, and then just return that x. And so we'll see more examples of this later. It's just sort of introducing you to what kind of ES6 syntax we're going to utilize in our functional code. The other thing, which is widely available in a lot of other languages, is default parameter values. Normally in JavaScript, we would have to just check if the value has, or if the parameter has a value, because essentially all arguments can be optional in JavaScript functions, and then we would have to assign later on. Well, with this, we can declaratively say, okay, if there's nothing passed in at this argument position, then go ahead and pre-fill it with this default value. So greet here has a name argument and a greeting argument, which we say has a default value of hi. So if I call greet with Scenic City Summit and hello, then I'll get back hello Scenic City Summit because I've passed in both arguments. But if I say greet with just Chattanooga, I have not supplied a value for greeting, so it'll use the default value, which is hi, and we'll just print out hi Chattanooga. One of the other things, and this isn't necessarily a syntactical thing, but it's just a new function available in ES6. And you've probably seen something similar to this from Lodash or underscore called assign. And it's on the object in JavaScript. And so what it basically allows us to do is just to merge multiple objects together. Whatever argument is at the first position will be mutated. So typically we'll just pass in an empty object here. And then what that allows us to do is pass in a variable number of other objects and just merge them all together and then give us back a final object that has all the keys and values from the other objects. And whatever objects come last in that chain will override other values if they happen to have the same key. And we'll use this later in an example as well. And then finally we have ES6 classes. We in fact won't use these in the functional code, but we'll use it to contrast with some object-oriented code. But I still want to make sure you're familiar with this ES6 class syntax. So it's basically just syntactical sugar for constructor functions from JavaScript. There's nothing really special about them. So this class point, I can define a constructor method, and it takes some arguments x and y and assigns instance variables. That's the same as just a constructor function called point. And then that moveBy method on the left, that's the same as if I had just assigned a moveBy function to the points prototype. And so we'll see this later and contrast it with some functional approaches. So that covers some of the ES6 syntax that we're going to see, and we'll see them plenty more coming up in our examples as we look at the functional code. So now returning back to our principles, we want to first talk about predictability. And we said in this predictability, we have pure functions. So we want to see, what does that mean? What does it mean to be a pure function, and what's important about that? So a very simple example is this add function. It takes x and a y, returns x plus y. This is a pure function because all it does is it depends on its arguments and produces a value based on those arguments. It does not have what we call side effects. It does not depend on global state. It does not mutate global state. It doesn't even print to standard out, which we also consider to be a side effect. And what that gives us as a pure function is this guarantee that every time I call add with 2 and 3, I always get back 5. And that's another property that we like to call referential transparency. And that's just a fancy way of saying that I know every time I call this, I get back 5. So in fact, I could replace calls to this particular invocation with just the number 5, and it would not change the meaning of my program overall. And so it's a guarantee. That's why what's so important about pure functions. If they don't have side effects, we know they produce the same thing every time, then we have better assurance that our program is correct. So what then is impure? Well, we have this contrived example here of some functions of an API that depends on this global variable called name. And we're using a let binding, so it can be mutated. It can be changed, the value of it. So each of these functions are impure. GetName is impure because it depends upon that global state. If that global state changed, which it can because of the setName function, then we no longer have a guarantee that GetName will always produce the same values. Therefore, it's an impure function. Similarly, like I said, setName is impure because it mutates and changes that global state. And then that bottom function, print_name, well, it's impure for a couple reasons. It depends upon the global state again. We're printing out the name uppercase, but it's also printing to the console, which technically we would say it makes it impure because we could think of standard out as just some more global state that we are affecting in our function. So why does it really matter? I mean, is this that terrible to write impure functions like this? I would say it can be a little harder to test it. And that's what I think is so crucial about pure functions. So if I wanted to test this particular API and test the print_name function, well, first I need to make sure that I mock console log so I can track calls to it. And then I gotta make sure I restore it after every test. So then I can print_name, I can check that console log was called with uppercase Jeremy. But notice that the functions I call, my API, are separate from the assertions I need to make. So I have to do more due diligence on my part as a programmer to remember I'm mutating some state, so now I need to check that this particular function was called with this particular argument. And so it's putting more burden on us, and it's making it slightly harder to test. Now, this is an easier example, but you can imagine more complex examples with asynchronous things, how mocking can get pretty frustrating and annoying. So one thing I like to say about this is that we have a lot of hidden state, and that's uncertain state, because we have to say setName, print_name, we're doing all these mutating functions. We have to remember that some state is changing behind the scenes, and that can make it harder to test. So what would be the remedy? If we wrote it in a pure fashion, testing suddenly becomes a lot easier. So now I just write an upper_name function. It takes a name, and it returns name.toUpperCase. That's easy to test. It's a pure function. I know that if I pass in Jeremy, I get back Jeremy uppercase. If I pass in Jet, I get Jet uppercase. And so that's one of the beautiful things about writing pure functions and trying to do that as much as possible in our programs. It's a whole lot easier to test. We're just testing inputs and outputs. So moving forward, we talked about purity. We also talked about when we have this predictable principle that we have declarative programming. And to understand declarative style program, we need to first look at what is called imperative. And this is something we're probably already doing. And it's this idea we tell the computer how to achieve a particular result. And what does that look like? So if I had this double numbers function, it takes an array of numbers, and then it's going to produce a new array of numbers where every number has been doubled. Pretty simple. So we'll create an array to hold all these values. We'll do a for loop where we're incrementing some index variable. We'll push those into the new array where we double them, and then we return it. But we'd say this is an imperative style, and if not for the function names, it might take us a second to read through the source code and know, oh, this function doubles numbers. And you can see we're just giving a set of instructions to the computer. It's not declaring what we're really doing here. So what is declarative then? Well, declarative is, instead of saying how to do it, we're saying what we need. Declare what our result we want. And this is something you're probably already doing too, whether you realize it or not. If you do a lot of database queries, SQL, that's a declarative language. You don't tell the database engine how to get the data set, you just tell it what data set you want. Or if you're a front-end developer, HTML, that's declarative language. You don't tell the browser how to paint it, you tell it what to paint, what you would like it to look like. So how do we apply that then to JavaScript and functional programming? Well, now we can write 3 lines. We can do the double numbers with the native map method on the numbers array. So we take the numbers, we call numbers.map, we pass in an arrow function, and we can look at this pretty quickly, even without a function name, and say, oh, n maps to n times 2, and we're mapping that for every item in the array. That's a very declarative thing. We don't know how maps implemented internally by V8 or SpiderMonkey, but we know this is what we desire as our result. And just to kind of tie this back to what we discussed with the mathematical roots of this, we can see that we're mapping from a certain domain, a subset of 1, 2, 3, to a range subset of 2, 4, 6. So this is a very declarative style, and it makes our programs more predictable because we know they're pure, we know that they are written in a declarative fashion, we can reason about them better. So now, moving on, let's go to state. We talked about the principle of safety, and that was immutable state. And the idea is we don't want to mutate our state. We don't want to change properties on objects. We don't want to change items in an array. Instead, we would prefer just to create new state if we need to change it. Don't mutate what we have, because that could lead to subtle bugs and issues in our programs. So here's an example, very contrived example, but let's say I have an array of hobbies, programming, reading, music. And then let's say I want to grab the first two out of that. I want to log them out. That gives me programming and reading. That's fine. And then later on I want to print out, again, what was in the hobbies array originally. But now I'm getting back just music. So what was the problem here? Well, in this case, I just had a slight typo, but I had a mutable state. I used the splice method accidentally instead of the slice method in JavaScript, which normally just gives you a copy, a new array, with the indices that you specify. Splice is similar, but it will mutate. It will change the original array and just cut out those values from the original array. So this is an instance, very contrived, where subtle issues can happen in our programs and where mutability can trip us up and we don't realize it. So there's a couple things we can do to alleviate this. Back in ES5, object.freeze was introduced, which is a function that allows us to, as the name suggests, freeze an object or an array and prevent it from being mutated. And so that's a nice approach to utilize, and we'll see that in a second. Another approach that I highly recommend is immutable.js, which is a library from Facebook, and it has a lot of immutable data structures that you can utilize. So if we wanted to apply just the object.freeze, all we need to do is call object.freeze on our array. And now, when we mess up and we mistype slice and we put splice, it's going to throw a type error. So at the very least, we're going to get an error to say, hey, you may not meant to do this because you have a mutable state and you don't want to mutate it. And so hopefully we can catch this bug earlier because of that. And so immutability can give us these sort of safety guarantees to a certain extent and help us out a lot in our programs. So another thing, as we talk about safety, we talked about also transparency. We want our state to be transparent. We want it to be out in the open. And what that means is if we think of object-oriented styles of programming where we stuff our state behind an object, we send it messages, and we mutate that state. But as we saw earlier with some of our testing code samples, it can get harder for us to reason about what's happening in our program. We have to remember how these things mutate our internal state. So returning back to that point class, this is a classic example. We set a point at the origin, and then we want to move it by certain dx and dys. But it's all mutating something underneath. And that can be harder to reason about, like I mentioned. And not to mention, when we deal with mutable state, we might run into certain bugs that we didn't anticipate in our programs. So how do we approach this then with functional programming? Well, the idea is to just expose our state. Don't mutate it, keep it out in the open, and have explicit flow of data. So now instead of using a class, let's just have a create point function. It takes the x and a y, but let's just represent it, our coordinates, as an array of two items, kind of like a tuple. And we'll also freeze it to keep it immutable to make sure we don't accidentally mutate it. And now when we want to move the point, we won't change the values in that array. We'll actually produce a new array. So move point by, notice we're going to use that destructuring syntax that I used earlier. So when I pass in the point, I'll go ahead and destruct the array back out to the x and y coordinates. I'll also take the dx and the dy. And then I can add those, create a new array, freeze it again. And now when I create the point, if I want to move it, well, I just need to go ahead and create a new point and keep that state more out in the open and have this explicit flow of data where instead of mutating stuff underneath, we just have functions that operate on data and produce new data. And so this can give us other guarantees on how our data is flowing through our programs and we're not hiding as much behind objects. So looking at immutability, the safety guarantees, transparency, there are definitely pros and cons. So we've mentioned some of these pros. We have safety. We saw with the hobbies example where we can maybe catch bugs earlier because we're using a mutable state. If you have used or have heard of Redux, one huge benefit of it is that it forces you to always produce new state in your applications. And so if you use Redux dev tools or something like that, you basically get free undo redo logs for free. And that's really nice because since it doesn't let you mutate your state, you just create new state, you can hold on to that old state, and that makes it easier to debug your programs if you need to go back in time, essentially. We saw we have explicit flow of data too, so we can reason about what's going on in our programs a little easier. And then I have a couple points there which are caveated. We say less memory usage, and we'll see what that means in this next slide. But we also say we have some concurrency safety. Now, JavaScript's single-threaded, but we can still run into race conditions. If we have potential multiple asynchronous actions out on the wire, and maybe they're going to affect some shared state, if they don't change the state in a certain order that we expect, then we can still run into race conditions. But if our state's immutable, and we don't want to mutate it, then we don't have to worry about that. So we have concurrency safety already. Now, some of the cons, which I'll admit, there is a little more verbosity. We're bringing our state out in the open. We're not hiding it behind objects. We don't have these always nice, clean interfaces where we just call some method and we know the state that's hidden gets changed. If we're creating new objects, then that also means there's potential for more garbage collection, and actually there's potential for more memory usage, which is at odds from what I said earlier. But these are caveated as well, especially if you use a library like Immutable.js. If you use something like Immutable.js, it's smart enough to, when you create new objects, to know how to sometimes share the underlying data between two objects. Because it's immutable, you can share that data. You don't have to worry about something mutating it and breaking it. And we won't have time in this talk to really dive into Immutable.js, but if you're curious about functional programming, I highly recommend checking it out and utilizing it. So now we've talked about state, and we've talked about things like purity and declarative style programming. So now that we have some of that foundation underway, let's start looking just at functions and how we can see important properties of functions in JavaScript, and especially in functional languages, that empower us to do some really cool modular style programming and just treating these as small atomic pieces. So this first thing we'll talk about, it's pretty much a given, whether we realize it or not, is that this idea of first-class functions. JavaScript has functions as first-class citizens. So what does that mean? When I do this, const multiply equals some anonymous function, the fact that I can assign a function to a variable is actually a very powerful concept, whether we realize it or not. This means it's a first-class citizen in our language. No different than a Boolean, a string, a number, because I can assign those to variables, I can pass them as arguments. I can take a function declaration, I can alias it to some other variable binding. And like I mentioned, we can pass in functions as arguments. And we've probably been doing this for a long time, especially if we're JavaScript programmers, but it's nice sometimes to sit back and think about, wow, this is actually very powerful and a very useful thing. Many languages years ago didn't have something like this, and it's very empowering to have it within our repertoire. So we can build upon that, especially in JavaScript, and utilize what's called closures, and you've probably heard of this. But it allows us to encapsulate certain state. And that's what we're going to need when we want to start looking at, in a few minutes, partial application, currying, and composing functions, which allow us to do this building up to higher order patterns from very small pieces. So what is a closure? If I take my add function from before, and now I'm going to separate out the arguments, I'm going to create this create adder function. And notice all it does is it takes an x argument. But now it's going to return a new function. Again, I can return a function because it's a first-class citizen. And we in fact would say that this create adder function is a higher order function because it returns a function as a value. So I return this new function. It takes a y as argument. And then inside, we finally do our computation x plus y. So we can kind of delay our computation, but we can use this as a small building block to build other functions without explicitly writing them. So I can create a function that adds 3 to whatever's passed in just by calling create adder with 3. I'm essentially filling in x to be 3. And notice, inside that second function, when I invoke that at the bottom, I'm referring to that x that was passed in earlier. That's a closure. I'm closing over that x reference right there in that later function. It's able to remember what that value is and utilize it. And that's a very critical concept that we'll utilize as we keep building on these foundational patterns. So what's a more practical example of this, for example, to look at? So say we have a request function, and that's just responsible for wrapping over the fetch API, which is essentially a nicer way of doing XHR calls to our API endpoints. So I can call a couple API endpoints, but let's say I have these custom headers I always need to send up to my API. Well, that could get slightly repetitive, so of course I could just write a function that always passes those headers up. But we would like for this to be more general purpose, ideally. So one approach we could do, and I will caveat that technically this function isn't pure, but what we could do is we could take that same concept we did with createAdder. We could take options as an argument, and then we can return another function that will take other options. And then we'll finally call the original request function, and we'll use object.assign to merge all those in. So all that is a fancy way of saying I want to go ahead and pre-fill some defaults, some shared options. In this case, my custom header that I want to use. And that reduces that duplication. So that's one benefit of using closures. We can reduce some of this duplication. And then I can just invoke my different APIs with their URLs. So there's where we take the options and we can refer to it inside that inner function. So these first class closures, they are going to be this foundation for these higher order patterns that we're going to start diving into now and looking at. So the first thing is partial application. And what partial application is going to do is we can ask the closure and say, well, I have this createAdder, I have this createRequester, and I could keep doing this pattern over and over and over, and it's going to get a little tedious. So what if we could have some more general purpose way to essentially fill in those X or fill in that options? And that's one thing we can do with partial application. So we could return to saying add is just a function that takes X and Y and returns X plus Y. And then let's say we have this hypothetical function called partial. And we can pass in add to it, again, because these are first-class citizens in our language. And then I can pass in 3. And what I'm saying is take this function, whatever its first argument is, let it be 3. Pre-fill it with 3. And that gives me back this add3 function that when I invoke it, all it needs to do now is fill in its argument with Y, and then I can return the result. Same thing with the request function. We could do the same thing. If we had this hypothetical partial function, I could call it on my request function. And now what I'll do is I'll have it take 2 arguments, a defaults and a options. And then we'll just merge those with object.assign. But I can use partial to pre-fill in those defaults, whatever shared options I need, my custom headers in this example. So how would we implement this partial function that we keep talking about? Well, it's actually very simple to implement with ES6. And also, if you are a big Lodash or underscore fan, partial is also available in those languages if you don't want to implement it yourself. But we can take 2 different approaches to it. The first approach is we can actually utilize something that's already natively available in JavaScript. If you've heard of the bind method on functions, what it normally does is it allows you to bind the this context in JavaScript. And if you've done JavaScript for quite a while, you have probably run into issues with this. So you can use that to just say, set the this special variable to a certain context. One not very well-known thing about bind, though, is any number of extra arguments you pass into it can actually be partially applied arguments. So it essentially does what we just saw in those previous slides with the hypothetical partial function. So what I can do is I can just capitalize on this. We're not worried about this. We're functional programmers. We don't want to use this. So we'll just pass in null for that first argument. And then we'll use the spread rest operator here to just pull in all the variable number of arguments that we want to partially apply into this function and just pre-fill their values. Now, if we wanted to handwrite it all ourselves, it's not that much more complex. We just utilize the rest spread operator a little more. So again, we take a variable number of arguments after our function. We return another function that takes in additional arguments, again, variable number, so we'll use the rest operator. And then finally, we can invoke the original function. We can do that. It's a closure, so we're referring to it when we originally passed it in. And then we just make sure to pass in first all those pre-filled arguments, the args variable, and then pass in the other args that we just passed in. And so that allows us to accomplish our own partial function in pure JavaScript. So now let's take that concept a little further. what would be really nice is if actually we didn't even need to call partial on some function. It would be nice if our functions just sort of had this concept built into them already, where they could partially apply on their own. We don't have to manually do that. And that's what we call currying. So there's that subtle difference. So what that means is, with currying, what I do here, see, is I call add, and I only pass in 3. And that's going to go ahead and pre-fill x to be 3. So what this is smart enough to know is that you haven't given me all the arguments yet. So I'm just going to go ahead and fill in what you have given me until I have all of my arguments satisfied. And that's what happens when I then evoke add 3 with 2 and get back 5. I could apply the same concept again to our request function. Pre-fill any default shared options, such as the headers, and then invoke it again with our API endpoints. So how do we accomplish currying with JavaScript in ES6? Well, little secret, we already did it earlier with the createAdder function. Only thing is, I wrote it differently. What we're doing now is we're just writing it in one line, using the arrow functions, and just using that single expression body, at least for this add function. So notice here, we have 2 arrows. That may be a little confusing, but let's just take it from left to right. So first, add takes the x. That's what we saw earlier with createAdder, and it returns a new function that takes a y. We've just elided the braces this time, and we've put it all on one line. So we take the y, and then we have another arrow which maps then to x plus y. So the basic general rule of thumb you could think of this is that instead of using commas to separate our arguments, we'll just separate them with arrows, and that essentially gives us a rudimentary curried function. And then at the bottom, just so you kind of see what's happening, there's the old ES5 version of this function, where we just declare a function, add, and then we see where we return an anonymous function that takes a y. Same thing with the request function that we've been using in our examples. Separate our arguments with the arrows, and that gives us this nice curried function where we can just build in partial application automatically. So it's really powerful, wonderful concept. So this is all well and good, nice, interesting topics, but is it practical? Is it useful? How could we really use this in real code? So let's actually piece this together and see a not unrealistic example of how this might be useful and how we could take small building blocks to solve a slightly harder problem. So I have this contrived example where we're going to basically query an API for a shopping cart and whatever items are in the cart. And what I want to do is I just want to take the price of each item, apply a discount, and apply the tax rate to it. And we're just going to use curried functions and promises to accomplish this. So the first thing is we're going to write a map function. And what we're going to do is make it a curried function. Its first argument will be the function that we want to eventually apply to an array of items. The second argument will be the actual array, and then we'll just delegate to the original array.map implementation. Remember, we saw that earlier when we wanted to double numbers. We'd call array.map, we'd pass in that function that maps n to n times 2. But we're just making this more general purpose here, where we can give it any arbitrary function to use. We'll have a multiply function. That's just like our add function. We're just doing multiplication this time. We're going to have this pluck function. And essentially what that does, this is actually a function in low-2 that does the same thing, but we're going to take a key, string, as the first argument. Second argument will be an object, and what we want to accomplish is just basically pull out whatever value exists at that particular key for that object. And so now here's how we can start utilizing these curried functions. Instead of writing a discount function, instead of writing a tax function, I'm just going to use my multiply function because I can express the discount, I can express the tax rate in terms of multiplication. If I want to apply a 2% discount, then I'll just multiply by 0.98 because that'll decrease by the 2% of the original price. Same thing with the tax rate. If I want a 9.25% tax rate, I'll just multiply by 1.0925. This is a curried function, so all I've done is I've filled in x. It's still waiting on that y, which will be the price that we'll get eventually. already seen this. We're using our curried request function to fill in our custom headers. And then finally, we'll make our API request. And then we're going to look at that a little more closer, but see how we're utilizing everything up top there to handle a lot of complex stuff down there on the bottom. So what we're essentially doing here is we make this request, we're using promises, it's going to eventually resolve, we're going to get back this response, an array with 3 items. Their prices are $5, $10, and $3. And then we're going to attach the then callbacks for the promise, and we're going to pass in functions to operate on this data. But look how essentially more declarative this can be. We can read this and say, okay, when I get this response, I know I want to pluck out the price, I want to map in the discount, and I want to map in the tax rate. So taking those a step at a time, remember pluck price, curried function, we give it a key, gives us back a function that expects an object. So we still have a function. Map expects a function, so we give map that particular function that's going to pluck out the price. And then once the promise resolves, the map function is going to finally supply the array, and it's going to map that pluck function over every item in the array. So there we can pull out 5, 10, and 3. Next, it's going to send down that array of prices to map discount. Again, discount we created by just invoking multiply once with the discounted rate. And then map's going to apply that to every item. And similarly with our tax rate, we'll make sure that we can just apply it all at once. And so this gives us a very definitely interesting way to do a lot of this complex stuff, but with very small building blocks that we just use curried functions to express this in a very pure and declarative manner. Now, one final thing we can do with this, though, is talk about composing closures, composing functions together, building upon curried functions. And if you've heard of this, you may remember, again, back to math, when you composed functions, say you had f of x and a g of x, and you compose them, you produce some sort of f of g of x or g of f of x. But the basic idea is, especially if maybe you've done some Unix shell programming or something, this idea of piping one thing to the other, where you have something that takes input, it produces an output, its output becomes the input to something else. So you're just chaining these together and you're passing data down the pipeline. And that's essentially what composing functions is. So if I had something like this, process word, and we're going to use we won't show the implementation of these functions, but we have hyphenate reverse to uppercase. They're fairly self-explanatory. Reverse will reverse the string, hyphenate's going to put a hyphen in the middle as best as possible. But I want to say apply all these functions at once. So what I could do is I could compose them together, take all the functions, chain them together to where it becomes one new function that applies all of these one at a time. And by convention, normally with compose, we would go from right to left. Now I will mention again, compose, this is not something built into JavaScript, so this is another hypothetical function, but it's available in Lodash and underscore. And there's actually a different version called flow, which basically does it left to right instead. And this can be implemented as well. I don't have time to show the implementation of this, but the slides online will have a basic example of how you could write it yourself if you're interested. But see, what I can do here is I can chain them together, and then I can again map over this array of words and apply each function one at a time to each item. I don't have to call it on my own. It just chained together for one function. And just to show you what that kind of looks like explicitly, is if I wrote it explicitly down there on the bottom, it's essentially as if I'd called to uppercase with word, and then just let that get passed into reverse, and whatever that produces get passed into hyphenate. But we've just made this a general purpose approach where we can compose them together and do it in a more declarative fashion. So how is this useful? How could we utilize it? Well, actually, let's go back to our example we just saw earlier with the shopping cart. Notice here what we had done. We had mapped over the array 3 times. So, sorry about that. So we had iterated 3 times. And in this case, it's not a big deal. We had 3 items in our array. But if we have something that's more performance intensive, maybe we're operating a lot of data, we may not want to iterate 3 times, transforming all these items in the array. So what we could actually do is just add composition to the mix here. So now we can make this a single iteration. Remember, map just needs a function. So I could produce a new function where I take plucking the price out, applying the discount, applying the tax rate, all composed together. That gives me one function that does it all together, and then give that to map. And that ensures that we can apply all these functions in one iteration instead of 3 iterations. So this can be very useful to just apply multiple things at once to array of items, for example. So we've done a lot with functions. We've talked a lot about state and mutability. One thing we haven't quite covered, especially when we think back to imperative style programming, is how to deal with the loop issue. Sometimes we have problems that we have to use a loop to solve it. And we've already said that loops, those are imperative. We use mutable state, and it's not something we necessarily desire to do in functional programming. So how do we tackle this particular issue in functional programming? Well, this is where we would incorporate recursion. And you've maybe used recursion before, especially if you're doing a lot of graph traversal type problems and whatnot, but it's a very powerful and declarative way to solve these type of loop issues in functional programming. And we essentially just want to solve a problem in terms of itself. So a classic example of this, if we go back to math, is the factorial. Remember, with factorial, we have a number, an exclamation point. In this case, 4 exclamation point, factorial. 4 times 3 times 2 times 1, that gives us 24. And in general, we would say that we have n factorial would be n times n minus 1 times n minus 2, and so on until we get down to 1 again. So if we wanted to solve this in JavaScript, we might take the imperative approach. We said, okay, well, this looks like I need a loop. So we could start an initial result value of 1, we do a while loop, where we multiply the result by whatever n is passed into the factorial, and we just decrement it, and we keep looping till we reach the end of the loop. And that works fine. But we don't want to do this in functional programming. We want a slightly more declarative approach. So instead, we could do this in a recursive manner, where we can write actually fewer lines of code, and we can actually express the problem closer to its original mathematical definition even. So notice here, factorial ends up calling itself. And notice it actually models that general representation of factorial that I mentioned earlier, n times n minus 1 times n minus 2, and etc. Except here, notice we have n times factorial of n minus 1. So it's essentially going to keep calling this recursive function over and over, doing the n minus 1, n minus 2, and etc. But eventually we need to stop, or we're going to get an infinite loop, and that's where we have what's called a base case in recursive functions. In this particular instance, we know we're going to stop at 1, so we're going to check whenever n is less than 2, go ahead and return 1. And that'll allow the answer to start bubbling back up and give us the final answer to the original call. So if we did this as factorial 4, remember, this is going to make a recursive call n times factorial of n minus 1. So that's 4 times factorial of 3. And that will in turn call factorial of 2, factorial of 1. And now we've reached that base case. Remember, n is less than 2. So now we can return the 1, and then we'll just start bubbling up the answer. 2 times 1, 3 times 2, and then 4 times 6. And that's how we can solve it in a very declarative, recursive manner. And this is a general approach you can apply to a lot of problems. And there's just a couple steps. If you have a math background, you did maybe a lot of inductive proofs back in the day, it's very similar to that. You need to find what's called a recurrence, kind of ties in with that word recursive. What pattern do you need to repeat? This is also very important in dynamic programming if you've done a lot of that. In this case, n times n minus 1 times n minus 2, etc. And then we need a base case. We just need to know where does this stop at so we don't have an infinite loop. So what's the performance story on all this, though? What if I wanted to call factorial of 100,000? What am I going to get back? I'll actually get back nothing. I'm going to have a range error maximum call stack size exceeded. So what is that actually all about? Does that mean that we can't do recursive functions, that this isn't going to work? Not necessarily. But what does it actually mean? So what's going on here? Let's go back and trace through these calls, and let's put a call stack next to this. So when we call factorial 4, imagine the call stack, we add in a stack frame for this particular call. We know it makes a recursive call to factorial of 3. So let's add a stack frame for that. Same thing with factorial of 2, factorial of 1. But notice what's happening here. Our stack keeps growing and growing and growing. Thankfully, we've reached the base case here, so we can start popping off the stack frames and getting back answers. But what happens when we do factorial of 100,000? So the stack grew order of O of n. So 100,000 calls means 100,000 stack frames. And then depending on what environment you're in, when I did some of these calculations, it was an older version of Node, but at that time, a stack frame was usually around 48 bytes. The max your call stack could grow would be around a megabyte, a little less than that. So 100,000 times 48, converting that into megabytes, we attempt to use 4.58 megabytes. And we were limited to less than a megabyte. So that's why we got this particular error. So does that mean we can't solve this particular issue with recursion? Not necessarily. So another thing in ES6 is this thing called tail call optimization. And it's a really powerful concept in functional programming where we could treat the problem, this recursive problem, if there was some way instead of growing the stack, we could just replace stack frames because we're basically solving a problem in terms of itself. And so the critical key point to this is we need to make sure that the recursive call happens in what's called the tail call position, which essentially means it needs to be the very last statement in our return statement. The very last thing that's evaluated in our return statement. So our original example, we couldn't optimize this for tail calls. And you might be saying, well, there's factorial, it's in the return call, it should be fine, right? If we follow the order of evaluation here, we have n minus 1, then we have factorial of n minus 1. But the last thing is we still need to perform this multiplication step. So we are forcing the program, for every recursive call, it has to wait on the recursive call to come back before it can finally produce an answer. Therefore, we have no choice but to keep growing the stack. But we could change how we define the function and make it optimizable. And what we're going to essentially do is actually just introduce another argument. And this is usually the typical pattern you use when you need to make tail call optimized functions, is you want something that's called an accumulator. And so we're going to call it accum for short. We're going to use the default value for the parameter and set it to 1. And so typically you want it to start off with whatever your base case return value was. We knew that was 1. So when n is less than 2, instead of returning 1, we'll return whatever accumulator is. But the critical thing here is now we've moved that multiplication to inside the recursive call. So we still have n minus 1, but now we're doing n times accum. And so as the name suggests, an accumulator, it's going to start accumulating the final result through each recursive call. So the order of evaluation here now, n minus 1, n times accum, and then finally now the factorial is the final statement in this return statement. And now we can optimize this. So what that means is, if I know that I can call factorial with a certain number, and it basically is no different than calling factorial with different arguments there on the bottom, then I could theoretically just replace stack frames. And we'll see that. So if we do it, we now can get back a value. We get back infinity, but that's just because of number overflow issues in JavaScript. But that means we can solve these problems to a certain extent still with recursive functions. So I mentioned, what does this look like now with the call stack? Well, again, we do factorial of 4. We have an implicit 1 there. Remember, we're just using the default value, so that's why I commented it out. So we've had this stack frame with factorial of 4 and 1. It's going to make a recursive call to factorial of 3 and 4, so actually we could say factorial of 4 and 1 is no different than calling factorial of 3 and 4. Therefore, I can just replace the stack frame with factorial of 3 and 4. Well, that's no different than calling factorial of 2 and 12, so just replace that. And that's no different than calling factorial of 1 and 24. And notice there on the right, we've been accumulating our answer. Remember, 24 was the final answer here, so we've just been accumulating it in that second argument position. And then we've reached the base case, so we'll just return that. And that's how we can solve these type of recursive problems still in an optimized way, thanks to this new feature in ES6. And I believe it's actually natively available now in the latest version of Safari, although Babel is able to basically do this for you under the hood if you want to transpile it as well. So wrapping up, we've covered a lot of topics here, and I just want to recap and kind of see what we've discussed and why it was important. We talked about some principles, predictability. We have pure functions. We have declarative style programming. And that allowed us to have better guarantees, better deterministic outlooks on how our functions are going to operate. And that helps us have better trust in our programs, that we're not necessarily always going to run into subtle issues and bugs, especially with mutable state. We also talked about this, safety. We want to use immutable state, create new state. We also want our state to be transparent and out in the open. We don't want to just hide it all behind objects that we send messages to. And then we talked about this modular concept, that we can take tiny, tiny pieces through currying, through composition, and we can build up more and more complex patterns and more complex functions just out of that and solve actually decent problems. So I just want to leave you with some final resources. These slides will be available online as well. This is Professor Frisbee's Mostly Adequate Guide to Functional Programming. It's becoming definite required reading for someone that wants to do functional programming in JavaScript. Brian Lonsdorf is very, very intelligent, smart guy, and I highly recommend checking this book out. He covers a lot more than I do, and probably more eloquently than I ever could, so definitely check this book out. We've been talking a lot about ES6 too, and if you want to utilize that, especially for older browsers, I highly recommend checking out Babel so you can transpile code into equivalent ES5 code that can run in older browsers. If you want to try out a different language that actually transpiles to JavaScript, I highly recommend these languages. Elm and PureScript are Haskell-inspired languages and very, very powerful languages, especially Elm's becoming much and much more popular. There's also ClojureScript, which is basically an implementation of Clojure for the browser. If you've not heard of Clojure, it's basically a Lisp that runs on the JVM. Some libraries that we've already mentioned before, Lodash, Ramda, great functional libraries. There's also RxJS and Bacon.js if you want to check out reactive functional programming. And then, of course, we already mentioned Immutable.js that allows you to have immutable data structures. And then for the MV star crowd, of course, I'm going to highly recommend React and Redux, which definitely espouse a lot of functional concepts. So if you want to potentially take this somewhere else, I would highly recommend them. At the very least, utilizing Redux to potentially handle your application state, even if you're using something like Angular. And with all of that, thank you all so very much for joining me. And there's links for codes and